So we're in section 3.5 and we're discussing exponential and logarithmic growth models. And let's look at our first example. The graph below shows the growth of the Mexico City metropolitan area from 1970 through the year 2000. So if you look at our x-axis where independent data lies, we begin at 1970 and this goes through the year 2000. In 1970, the population of Mexico City was 9.4 million. By 1990, it had grown to 20.2 million. So our dependent variables lie along the y-axis. In this case, our dependent variable is represented by population, and you can see that in 1970, our population is approximately 9.4 million, and by 1990, it had grown to 20.2 million. We're asked to find the exponential growth function. That means find the equation that models the given data. Because this is an exponential growth function, we know that our equation is of the form A equals the initial amount times e to the kt power. And if you watch the introduction to Goal 1, you can look back at your notes to see why we would choose this as our growth function. So if we want to find this, we know that we need the initial amount, and we also need k, our growth rate. K is our constant, and our initial amount is also our constant. So right now, I do know that the initial amount was 9.4 million. All right, so in the place of a sub 0, we will replace that with 9.4 for 9.4 million times e. We do not know our constant, the growth rate yet, but I do know that we have been calculating this for 20 years. So right now I can replace t with 20. I do not know k, but it is possible to find k. If we want to find the growth rate, we need to find what amount corresponded to 20 years. So we know that 20 years into this data, the population was at 20.2 million. So at 20 years, the population was 20.2 million. So we can replace A, the amount at 20 years, with 20.2 million. Okay, so we now have an exponential equation with one variable only. So let's go through and solve this equation. If I'm solving for the rate, I first need to isolate the factor or the base that's raised to that exponential power. So I need to isolate e to the 20k power. We'll do that by dividing both sides by 9.4. You're welcome to use your calculator to crunch numbers here. I want to caution you though against using your calculator to find this value, because if you calculate 20.2 divided by 9.4 and then round that answer, by the time you get to your final value for k, you will have estimated multiple times and will not have an accurate growth rate for k. So at this point, I'm going to leave 20.2 divided by 9.4 in the form it's in. We'll go back at the end and then calculate to get an accurate growth rate. So our current equation looks like this, and I still have k in the exponent. Well, in order to get k out of the exponent, I know that I need to take the natural log of both sides of this equation. So if we take the natural log of the left, we have to take also the natural log on the right. So let me get rid of 9.4 because we know it's going to cancel, or did cancel, and take the natural log on the right. Now recall our properties. Our properties of logs tell us that when we have the natural log of a base raised to the power, we can use the power rule to pull that exponent to the front. So when I pull that exponent to the front, my new expression is the natural log of 20.2 divided by 9.4, which is equal to 20k times the natural log of e. We know the natural log of e is equal to 1, so we can go ahead and cancel the natural log of e. Finally, to isolate k, we'll divide both sides by 20, and we can finally use our calculator to get an accurate value for our growth rate k. So let's use our calculator now. If you'll pause the screencast and find the value of k, and please round that to 3 decimal places. So we're finding the natural log of 20.2 divided by 9.4. And we're dividing that value by 20. And so we have a growth rate of 0.038. Because our growth rate k is equal to 0.038, we can now write an accurate growth model. So the amount at any given year is equal to the initial amount of 9.4 million people times e to the 0.038 times t power. Notice in our final expression, t, the independent variable, is in our model, and a, which represents in this case our population, our dependent variable, is represented. So you should always have a constant value for the initial amount and k, the growth rate, when you are writing a growth function. So let's answer this second question. By what year will the population reach 40 million? Does 40 million represent A, the amount at a specific year, or T, the year? Well, of course, that's going to represent A. So we'll replace A with 40 million, or 40, and 9.4 times e to the 0.038 times t power. Now to solve for t, we'll follow the exact same process that we did in the previous example. We want to begin by isolating the base that's raised to the exponential power, and we will do that by dividing 40 by 9.4. And that causes the 9.4 to cancel on the opposite side. How do we get the exponent, the t, the variable, out of the exponent? Well, we would take the natural log of both sides. We know that the natural log of e raised to the 0.038 t power, the natural log of e will cancel, and we now have the natural log of 40 divided by 9.4 is equal to 0.038 t. And we can divide this by the coefficient of t. And again, let's calculate and find this time the value of t. So 40 divided by, the natural log of 40 divided by 9.4, and that value is being divided by 0.038. So it looks like we get a value for t as 38.1. Now it's important to go back and read and make sure we're answering the question they're asking. The question says, by what year will the population reach 40 million? Well, if you answer 38.1 years, you're telling us in how many years we could expect the population to reach that, not the actual question that's being asked. So if this data was initially set up in 1970, then we would add 38.1 to 1970. And so we could say that by the year 2008, the population should reach 40 million, according to this model.